So as usual, we have student presenters in our seminar series. So today we have two student presenters. One is Caleb Weaver, and the other one is Kang Wang. So Caleb will talk about the single index models with functional connectivity network predictors, and Kang will talk about coverage of credible intervals in Bayesian non-parametric multivariate isotonic regression. So without further ado, I will hand this over to Caleb. Oh, well, I forgot one more thing. So each talk will be about 25 to 30 minutes, and we can ask questions either during the talk or in the end. So Caleb, are you ready? Let me stop share.
Sure. So let me just start sharing here. So if you would let me know when you can see.
Yeah, it looks very good.
All right, perfect. So thanks for joining, everybody. I hope everyone's doing all right. So today I'm going to be talking about some work that I've done with my PhD advisor, Lou, here in my time at NC State. This is one of my previous projects in which we look at single index models for functional connectivity network predictors. So this work, again, was joint with my PhD advisor, Lou, as well as his collaborator, Martin Lindquist, from Johns Hopkins University. So just want to give a quick introduction just to fMRI data and what functional connectivity actually is. So in an fMRI study, basically a subject puts their head in a big scanner with a large magnetic field that aligns the hydrogen protons in the brain, creating a magnetic signal strong enough to measure, basically. And so what it's trying to measure is blood flow in the brain, right? Because there is a correlation between neuron activity in the brain and blood flow. Basically, when a part of your brain's working, your brain needs to push blood there so it can keep working because the brain doesn't have its own oxygen storages. So that's what's being measured here in these time series plots. Along with that, there's a couple ways to classify parts of the brain. So one is by what's called functionality, basically. So here, there's three segments or three classifications of regions of the brain. This first one is called the default mode network, this one in red. So what that means is basically these regions work together to perform some function, some neuronal function. And in this case, for the default mode network, the idea is, well, you're not really actively thinking about something. You're kind of just drifting off. You're recalling memories. You're working through like a dry manuscript, and your brain just kind of starts drifting a little bit. Well, neurons are firing in your default mode network, and that's measured by blood flowing there. Kind of on the other side is the frontoparietal network, in which neurons start to fire when you're really thinking hard about a problem. Or you're doing some, working on a puzzle, that kind of thing. So you can kind of think maybe, they're kind of anti-correlated. And so that's quantitatively measured by what's called functional connectivity. So in this matrix here is the partial correlation matrix of 100 nodes or 100 regions in the brain. And these reference lines indicate the region's classifications. So for example, in this row, is the default mode network, that first region, first classification that we discussed. And so the regions in this block diagonal are all the nodes in the default mode network. And you can kind of see in the block diagonals, they're greater in magnitude, which you can kind of get a sense for how these networks are classified. And you can kind of see strong negative correlations here between the default mode network and the frontoparietal network. It's kind of what we expect based on what we know about them. So just an introduction to our motivating data set here. So we're looking at data from the Human Connectome Project on resting state fMRI scans. In this data set, we have 820 subjects, and we look at 100 of the brain regions, and we get basically fMRI bold signals, which is measure of blood flow, basically, over 60 minutes so resulting in 4,800 observations. And we also record 2 response variables, fluid intelligence and sex. And so 3 of those subjects are illustrated here. So these are the functional connectivity matrices of 3 of the subjects. This first one is male, this third one is male, and we have the fluid intelligence for all 3 increasing here. And so you can kind of see, I mean, they all look relatively similar because they're all human brains, but there are subject-specific differences. And so the idea here is how can we use these subject-specific differences to measure these responses? Can we do so in such a way that respects the network structure of these things? And what kind of assumptions can we put on such a model?
Can you talk more about the fluid intelligence?
Yeah, sure. So fluid intelligence is just something that the Human Connectome Project tracked. It's the result of the PMAT test. So they take a kind of an IQ-based test, and you get a numeric score. It's really a problem-solving kind of examination.
Okay, so that is an outcome.
Exactly. Yeah. So we're looking at two outcomes: sex and fluid intelligence, and our kind of predictor is this network here.
Okay, great.
So saying, based on this network, what can we say about the sex or the fluid intelligence of the subject?
Great.
So
I'm sorry, I have one more question too. So in this, right, so you said you have 100 brain regions, and so are you averaging over the nodes or voxels in each region, or are you considering them separately?
Yeah, so that's a great point. So we have the bold signals that 60 minutes for each of these 100 nodes. And so each of these points here is the correlation between, or the partial correlation between this guy and this guy. So if this is a region in the brain here, this single row here of the 100 nodes, and this is another one. So we're looking at this to be the partial correlation between this time series and this time series.
At one voxel.
At one voxel. Yeah.
Thank you.
Actually, I have a follow-up question to that as well. So what do the colors in your matrix mean then?
Yeah, so these are partial correlation values. So if you see a red, that's going to be positively correlated. If you see a blue, it's going to be negatively correlated.
Okay, so that has nothing to do with the fact that like the default mode network is in red and the dorsal attention network is in
No.
Okay.
Yeah.
And what pipeline are you using for this? Like you can take the fMRI data through a bunch of different pipelines to construct these correlation metrics, right?
Yeah, exactly. Yeah. So these are coming from like a parcellation done by the Human Connectome Project, and all we're doing is just taking we're using the graphical asset. But yeah, to get to that point.
So you are taking the voxelation that they have done.
Exactly. Yeah.
And the blocks are also given, like the way you are partitioning the matrix into blocks.
The designation of the networks is given. Yeah.
That sounds good. Okay, yeah. Cool.
Okay, so just quickly get through this. So what's previously been done in the literature is just applying, standard statistical methods, predictive methods to these kind of data to regress, a quantitative response on a functional connectivity network. Usually what's done is just vectorize it, string it out as a vector, and use those as individual predictors. But for one, that ignores the network structure of the predictor. And two, it's kind of hard to interpret typically with these kind of models. But there's also another branch of research that have tried to apply some sort of network structure or some kind of constraint that respects this fact that it's a network, respects the fact that it's a partial correlation network or matrix. And so, for example, Regularization et al. is particularly influential to us. They impose a type of structured sparsity in their coefficient matrix. And so we try to incorporate something similar. I'll show it in a moment. And then separately is the idea of single index models. So we're interested here in the case that there is a nonlinear relationship between response and these predictors, which is something that's not allowed, basically not assumed or incorporated in the models of these guys and these guys. So one approach for non-parametric regression in the case that you have high dimensional predictors like we do is to use a single index model, which performs basically non-parametric regression on a linear combination of the predictors, which again is helpful in high dimensionalities. Okay, so in our paper, we propose a model for performing this nonlinear relationship, or for modeling this nonlinear relationship in which our parameter space can be thought of as a network of parameters. We incorporate a structured sparsity in the estimated coefficient matrix. And the model and the algorithm are such that they're applicable to not just functional connectivity matrices, but more general matrix value predictors, and allows for other kinds of structured sparsity patterns. There's a little bit of notation here. So we say that yi is subject I as response variable. So in our case, it's either sex or fluid intelligence. We say that x is subject I as estimated functional connectivity network. And we consider this model in which G is a known monotonic function, F is an unknown unspecified index function, B here is an unknown coefficient matrix, and so we're modeling this this linear combination of the elements of B to predict Y. And we're going to incorporate two types of sparsity in the coefficient matrix B. And I'll just try to quickly illustrate these two types of sparsities. The first is called node sparsity, in which we're trying to induce sparsity in the nodes, obviously. So here we have a very simple network, and it's illustrated by this adjacency matrix and this network graph on the right. We have 8 nodes and currently edges between all of them, so a fully connected network. So we introduce a bit of node sparsity in this case. So there's sparsity in node 1, and we see that node 1 dropped out of the network here, and this corresponds with the idea of node 1. If this is our coefficient matrix, node 1 and all of its edges between all the other nodes in the network is not predictive of your continuous or binary variable, of your response variable. And we introduce a bit more until we get to the point where we are at the most node sparse situation, in which only node 7 and 8, the edge between them, are informative of the response. So the other type of sparsity is just edge sparsity, which is a little simpler. In this case, we're not trying to impose sparsity in the nodes, we're trying to impose sparsity in the edges. So you see here, we impose sparsity in the nearest neighbors, and the outer edges drop out. And just a bit more, until only the edges between these nodes are informative of the response. And so how we're going to estimate B and the smooth function F is to minimize this objective function. So we have this negative log likelihood of the function B and a regularization parameter or term R. And we have a few identifiability constraints that are kind of common to estimating single index models, as well as some based on the fact that we're dealing with symmetric matrices. So to impose that node and edge sparsity, we're going to use this term. So we're going to say RB is equal to lambda 1 times the sum of the L2 norms of B. So basically what this is doing is imposing basically a group lasso on the node coefficients, so that the nodes, coefficients associated with the nodes, are being shrunk towards 0 as a group. To perform edge sparsity, we're going to have this lambda 2 times the sum of the L1 norms, basically the absolute values of each of the coefficients. And in this way, we're going to shrink each edge individually towards 0. And so in single index models, it's more common to estimate F and B sequentially, just because this is a hard thing to optimize at the same time, basically for F and B. So Lou and Eric Chi have a paper with one of their previous students, Brian, in which they have a single index model for multivariate responses, and they perform this kind of sequential estimation procedure. And so our algorithm is inspired by that work. So we'll talk about those sequential estimations. So first, we're going to estimate F given B. So we're going to say, just for notation's sake, that TI is this index. So assuming that we have B, we can get this inner product of the X and the B's such that we have this G of the conditional expectation of Y. We're going to approximate F using a linear combination of B splines. And we're going to estimate the coefficients of these B spline basis functions using penalized splines. And we're going to use the second order difference operator penalty per Eilers and Meyers. And this is much easier than the next step. Basically, you can just use your favorite penalized spline software package. But with a fixed F, we're going to estimate the coefficient matrix B by minimizing this function. And so we solve this using an ADMM algorithm, which I might talk about if I have time at the end, but I probably won't. And so this overall minimization problem for both F and B is solved by iterating over these two steps. So we have some propositions around convergence that are similar to Brian's paper. And I won't get too deep into it, but we do have to deal with something called an overlapping group lasso, because you can kind of see for the node sparse terms, there's overlap in the coefficients. And so when one group goes to 0, the other group goes to 0. So you kind of have either a fully sparse or a fully non-sparse matrix in the case that you were using what's called the intersection of groups. So we use the union of groups method. So I might get into that a bit in the end if I have time. So we perform a simulation study here just to assess the performance of the model. So we're going to repurpose those functional connectivity matrices from the HCP data. We're going to consider 2 dimensionalities and 2 signal to noise ratios. And we're going to set the F function to be either linear or nonlinear. And then we're going to simulate continuous responses and binary responses parameterized by this conditional expectation. And we're going to use 3 types of coefficient matrices. The first is a circle network in which nodes are connected to basically only their nearest neighbor, a random network in which we impose exactly what we're looking for in terms of node and edge sparsity. We say that a node has 50% chance of being within the network, and then edges have a conditional 50% expectation, a conditional probability of 50% of being included, conditional on their associated node being included. And then finally, we look at a small world network, just a few examples of network coefficients. And we're going to set, obviously, the values all here are equal to 1. So in terms of comparisons, we're going to compare the single index model to just a linear model, in which basically we set the F function in our model to just be the identity function. And we're going to consider 2 other penalties, not just the node edge. So we're going to look at a lasso penalty in comparison, which actually is just the edge penalty. If you think about it, it's basically setting the node penalty parameter to be 0, and elastic net penalty, which takes just a bit of manipulation of the ADM algorithm to solve for. And so what we find is that there's no significant difference between the linear and the single index model, when in fact F is linear, which is not very surprising. But we do find that the proposed model has better predictive accuracy as well as classification rate when the index function is in fact nonlinear. And so classification rate here is defined by node and edge inclusion in the estimated coefficient matrix. So we find that even with the single index model, we have a similar predictive accuracy with the other types of tuning or with the other types of regularization terms, but we find that the node and edge term has better classification rates than both the lasso and the elastic net. So finally, let's check the time here. Oh, I'm good. So finally, we apply the proposed model to the motivating data set. So here we're looking at modeling fluid intelligence as a function of functional connectivity. So on the left, we have the estimated coefficient matrix, and you can see really clearly there's strong evidence of node and edge sparsity here, which helps quite a bit for interpretation. And actually, it's a little hard to see just because the elements are kind of so small here. But you'll see that relatively, the relationship between the connectivities between the default mode network and the frontal network have the most included edges, actually. And this kind of agrees with existing neuroimaging results that say that the relationship between the default mode network and the frontal network is indicative of intelligence. And so on the right, we have the estimated mean function from the single index model. And you can kind of see pretty clearly that there's a nonlinear relationship between the index and the response, based on the fact that we have this linear line imposed here. You can see how much it deviates And actually the R squared here for the single index model on a holdout sample is 36% compared to a 26% for a linear model. And the MSD reflects that as well. Okay. And so on the second page, we have a similar analysis of the sex variable. And again, quite a bit of node sparsity and edge sparsity. And actually the sex was very interesting, actually. So looking at an 80-20 split, using this coefficient matrix, you can predict the sex of the of the holdout set with an accuracy of 92%, which I think is extremely high for this kind of problem. So I thought that was very interesting. But on the right, we have the estimated mean function of the single index model. And because this is a logistic, a nonlinear, well, a linear, but a logistic function here, it's kind of hard to see the deviation, but there is actually evidence of slight nonlinearity here when you look at the metrics. Okay, so I got that through a lot faster than I thought, so I have some questions, but just to wrap up here, so software for implementing the model that I've just discussed is available at this URL. On my GitHub. The paper was published, I think, last year or earlier this year with biostatistics. So obviously more information is available there, along with supplementary material. And in terms of next steps, we're kind of interested in the application to other types of matrices, not necessarily just functional connectivity matrices, because the way that the model is proposed, it's not necessarily tied to the fact that it's a functional connectivity matrix. As well as other types of structured sparsities. And in terms of applications, we've looked at obviously resting state here, but the application to task-based fMRI is especially intriguing to me. So that's all I've got. So I do have some appendix material, but I'd love to see if there's any questions first of all.
Thank you, Club. So we have sufficient amount of time for questions. So now it's time.
Can I ask a question?
Yeah.
Okay. So great talk, Caleb. Really enjoyed it. Can you go back to slide 11? So I'm trying to understand this regularization that you are doing here. So why is the first one a node sparsity regularization and the second one an edge sparsity regularization?
Yep. So I'll start with the second one because it's much easier. So obviously this is just a lasso, really. You're penalizing the absolute values of each of the elements. And so if you're looking at one of these coefficient matrices, you're penalizing literally this blue element. So it's shrinking to 0 on its own. The red one, the node sparse term. So I look at the inside of here. So this is just the L2 norm of a column or of a row, because it's symmetric. And so this is a group Lassell penalty. So as lambda 1 is increasing, each of the nodes or each of the columns or the rows of the matrix is being shrunk as a group towards 0. And so because the column or row of the coefficient matrix represents a node, we call it node sparsity.
Okay, very cool. Yeah, so and this is something that you have done. Like this was not known before, like to do this kind of regularization?
No. So this has existed. So this has existed in like network research before. And one of my previous references, the Regularization work, actually applied it to neuroimaging. So that penalty term is not new.
So I have one quick follow-up. So if you are doing the regularization like this, you are kind of uniformly regularizing the entire network, right?
Yeah.
So every node and every edge. So for example, if there are some nodes that are already kind of very loosely connected to the network, you might remove them because you are treating them at par with some of the more highly connected nodes.
Right, exactly. Yeah, so a node has to be important. Basically, I mean, if lambda 1 is large compared to lambda 2, then the whole node has to be very predictive, not just one of the elements. That's the idea. Yeah. So we have thought about things like maybe including some sort of adaptive penalty to allow for correcting for something like that. But yeah, no, that's a good point.
So yeah, so if you had, I mean, a lot of node and edge heterogeneity in the network, then I mean there might be a bias. You might be like penalizing some of the weak nodes so that they don't even get to have any say in the model.
Yeah, it is a good point. It is a good point. Yeah, that's right.
Okay, very good. Thanks.
Have you compared?
Oh,
sorry. Go ahead.
Okay, I have two questions, so I hope that they won't take too long, so Shu, you can answer your questions. So the first is a question about the numerical stability. I wonder if you have any issues kind of at the boundary here. You have this, a lot of correlations that might be really close to the -1 and 1, and I wonder how the ADMM handles that. That's the first question. And then the second question is, is there a way of incorporating in particular like the spatial relationship? Right, so for example, nodes that are more or less further away might inherently have stronger or weaker dependencies, but maybe you would want to take that into account somehow in your framework as well.
Yeah, those are both really good. So let me start with the first one, and I'll probably forget the second one, and you can remind me. So the first one is about boundaries. I think that's a really good point. So we didn't do too much of the asymptotic work here, but I'm sure that if we did, we would have to assume that the values were not at the boundaries, because at least with our data and our simulated data, we didn't have, let's see, all of our correlations are basically within, this kind of bound. We don't have partial correlations that are necessarily 1 or -1. And I can't imagine a case, at least in functional connectivity, in which you would have such an element unless you had a very granular parcellation. But I think it's a good point. Yeah, if we were looking at things that, had the chance of being at the boundaries, I think we would have to, rethink the algorithm. Yeah. And so the second one, I think you were saying incorporating spatial effect to the model. I think that's also really good. So with our data, we don't have an idea of closeness, of spatial closeness. But I think it's really good. I mean, we've already got kind of a lot of terms here, and if you look at the ADMM, there's a few extra ones because of identity constraints. But I think it would be great, to think about, if it's not necessarily the what's driving the heterogeneity is being in a node together along with other edges, but it's the fact that you are in a region that's really close to another, or you're really close to another node. You might incorporate some sort of maybe like a fusion lasso or something like that to incorporate your neighbors. I think that's really good. But yeah, at least with our data, we don't have that effect because we don't have the locations. But yeah, I think that's really interesting.
Great, thank you so much. It was an excellent talk. Thank you.
Thank you.
Yeah, Emily's question, the second one is actually my question, like how to take into account the spatial structure in the brain. But
it's a very good question, and it's a common question. I really wish that we had had that artifact in our data, because I mean it's really an intuitive thing.
So may I jump in? This is Lu.
Yeah, go for it.
Me?
Yep.
Yeah, I think the spatial information, yes, we can have that, but we didn't look into that in this particular project, because this parcellation networks, there's a certain way you can actually quantify, at least from spatial perspective, how close they are. And I think one way we might be able to consider to incorporate is to some sort of like maybe fuse lasso, to sort of like push the coefficients towards to each other. But certainly that are gonna complicate this optimization problem, right? So, in terms of Emily's first question on the ADMM optimization, I think for several projects we have done ADMM, and for most part it seems to be working really well, except in one particular high-dimensional covariance matrix project where we use the FANTOP. That project seems to be having a little bit convergence issue, but it feels like for regression types of problem seems to working really well, even though we have multiple parameters here. But that's just our experience. Yeah.
So Luo, just real quick. So if you're using some kind of brain atlas in the parcellation, like the DS2116 or something like that, they do come with spatial coordinates. So
In some way, you can impose something like that. There's a way you can measure sort of like the closeness between the different networks.
Also some of the and also some of the newer pipelines. I think the Vogelstein paper mentioned here might be that pipeline, the migraine pipeline. They also have a lot of spatial information.
Yes, that's right. Especially because the way the regions are classified is according to their functionality, which is on the different networks, but the regions are spatial regions. So within each network, you have multiple regions, so they can be close. Most times they are close. As I think in the first slide, in the first introduction slide by Caleb, you can find that you see, they're relatively clustered together. Even though sometimes they can be a bit far away, but I feel like maybe there's a way you can quantify that closeness. For sure.
Sorry to interrupt, but it's time to move to the second talk. So thank you, Caleb, for the presentation. Now, can you show the slides?
Is that good? Thanks everyone for coming, and today I want to talk about Basin multivariate monotone regression and the study its coverage by developing the weak limit theorem. First, I will give a general introduction to the nonparametric multivariate regression problem. Then I will introduce our Basin procedure, and then the third section, I will introduce the weak limit theory we developed, and based on the theory, we can study the frequentist coverage of credible intervals. And then I will give some numerical results on the asymptotic distribution. Finally, there's a little conclusion for this work. So we consider a conventional nonparametric model, and we assume the error is normally comes from a normal distribution, and the covariates of dimension d. It is RID with a Lebesgue density bounded away from 0 to infinity. X and epsilon are usually independent. But the true error distribution can be RID sub Gaussian with mean normal. Before we define the monotone function class, we need a partial ordering on RD. The partial ordering we considered here is a Euro extension from univariate case. X smaller, the vector x smaller than y if and only if the coordinate of x smaller than the corresponding coordinates of y, and then with this partial ordering, the monotone function class is just a coordinate-wise increasing function class, and it's denoted by script f. So our objective is first to devise a Bayesian approach to multivariate monotone regression. As far as I know, little work was done in Bayesian society, and then based on a weak limit theory, we can study the frequentist limiting coverage of the pointwise credible interval. So for the prior construction, generally there are two ways. First, in our shift restriction regression problem, we can impose prior complying with shift restrictions. It is conceptually appealing because if the prior is in compliance with the shift restriction, and so will the posterior. But even we can construct such a prior, its theoretical property is how to analysis. We can hardly get the analytical some closed form posteriors for this prior. And also we need to design some specific computational algorithm. And the other way is using the at the prior construction stage, we can use the unconstrained prior, and this is a lot more easier because we can use conjugate prior and get the unconstrained posterior easily, and then by various like monetization algorithms, we can convert the unconstrained posterior to the constrained parameter space. So the second, we will take the second one to develop our Basin procedure. Basically, there are two ways to convert the unconstrained posterior to the constrained parameter space. In the abstract sense, suppose theta is a parameter space concerned here, and it might be Hilbert or just Euclidean, and we have some qualitative prior knowledge about like the shape of the regression curves or regression surfaces, and the parameter, the feasible parameter belongs to a closed and convex set denoted as theta R. It's a subset of the parameter space theta. Usually we can directly putting prior on theta R is very hard. So we consider impose unconstrained prior on theta, and we can easily obtain the unconstrained posterior because using something using conjugacy and the conventional technique. But the unconstrained posterior samples may not be satisfy may not satisfy the shape restrictions, and then we will perform a projection. Here we call the projection operator P theta R. So we project the posterior unconstrained posterior to the constrained parameter space parameter set. Thus, we can first we sample from the unconstrained posterior and convert the unconstrained posterior sample to the constrained parameter space. The induced posterior and thus induced projection posterior. Our inference is based on the projection posterior samples in practice. Sometimes the projection posterior doesn't behave very well. We need some generalization or relaxation to the projection operator, but return some nice property. The general immersion mapping we denote it as I from theta to theta R, and a property inherited from the projection operator is the composition of I with itself, is still I. After we impose the shape restriction, unrestricted posterior, we reduce this reduced to the immersion posterior. And in our in this model, we use piecewise constant function to approximate the function class. F belongs to Kg. Kg is an unrestricted piecewise constant function class, and Rg is a partition. We can here we take J is deterministic. It will depends on the sample size and also the smoothness, local smoothness of the true F. The only random quantity here is theta J. We can put a prior on Kj by imposing prior on theta J. Because we use a normal regression model, we can put independent Gaussian priors to the coefficient of theta J. And another parameter is sigma square. Sigma square we can either estimate using the marginal MLE by integrating out the theta and plug in, or we can use it. We can follow a fully Basin framework, use a inverse gamma prior, which is conjugate. As I just said, this Gaussian priors is conjugate, so we can generate posterior and restricted posterior sample very easily. But to map the unrestricted posterior sample to the piecewise to the Fj. Fj is the piecewise constant monotone function class. We need to define some suitable immersion mapping. And I will digress a little to talk about why we will define the immersion mapping in that way. First, the projection estimator, which is the least square estimator in multivariate isotonic regression or multivariate monotone regression. It's just it's just to minimize the squared Euclidean distance between observed response and the candidate F evaluated at the observed covariate. This estimator enjoys a max-min formula to characterize the solution. Fn hat is evaluated as at x0 is there's this max-min expression. We take minimum over all. L is a collection of all lower level sets, and U is a collection of all upper level sets. And upper level set is the is defined as the x such as fx greater than or equal to a constant. F comes from the monotone function class. So this collection is very large because F only need to satisfy the monotone shape restriction, and there are very lot of monotone increasing function 0 to 1, and L is lower level set. and this can be defined similarly, and its is x such that fx smaller than a constant. And this formula and this estimator doesn't change if we exchange the order of maximization and minimization, but even there are rich distributional results locally or globally in univariate setting and frequency literature, but no distributional theory exists for the multivariate isotonic estimator. So the reason we don't quite clear what the reason is, but we can see from the maximization and the minimization that the collection is very large, and we can hardly expect a uniform central limit theorem for the partial sum process. And recent estimator raised by Fugano's 2020 is they modify the maximum formula for isotonic estimator by only take maximization and minimization over or block hyperrectangle shaped upper level set and the lower level set, and this collection, this sets in the upper in script U is indexed by each U smaller than x0, and the set in L is indexed by every point greater than x0. And with this definition, we can expect some limiting distributional theory, and this was developed in Han and Zhang 2020 paper. But the block estimator is not is usually different when d greater than or equal to 2 if we exchange the order of max and min, which is different from the LSE. So we define the immersion mapping, but not the projection from Kj to Fj, and we denote the map by iota, and we consider 3 immersion maps here. The first one is max min, which use max min formula, and the second one is min max. The third one is just to take the average cost to neutralize the effects of the order of maximization or minimization, and then we the function take average over nj take average over the function value in the restricted subscript set. The out1 f is because we take minimization first and then take maximization. It's usually smaller than out2, provided all the nj, the number of coordinates, observed coordinate in ij, provided all the nj greater than 0, and also if f itself belongs to the monotone piecewise constant function class, and out f equals to f itself. A straightforward computation algorithm is just run over or J2 takes for fixed at J1, run over or J2 and compute the average, and then take minimum. and for each J1 and take the maximum. So this is straightforward. You just using the min max max min or min max formula, and until now, Basin inference can be made based on the immersion posterior samples. But we want to study if we can find the weak limit and study the frequency coverage. Yes, we can. So the assumption we make here is just X is an interior point of the 0 to 1, and we allow different local smoothness level alpha k. Alpha k is the first non-zero. Is the order of the first non-zero derivative of f0, and for simplicity, we assume all alpha k is for strictly more than infinity. That means f locally depend on all the coordinates, and f is locally continuously differentiable to the order the maximum of alpha k. One example is f or here I give an example of two-dimensional function, monotone function, and at the point 0 0.5, the smoothness level for the along the first coordinate is 3, and the second coordinate is 1. With this assumption, we also we need to define some the local contraction rate omega n, and also the rate along each direction adapt to the smoothness level, and here G should satisfy the this restriction, and JK is greater than 1 over RK. RK is the rate along the direction K. So we need partition finer than the inverse of the convergence rate, and also the product of JK. I mean the number of the cardinality of the partition cannot be too large. We need the desired contraction rate for sigma square. This L star is an index set. This index is also adapt to the local smoothness level, and IK is the order of the derivative along the case of coordinate, and we can expect the weak limit theory. The posterior, the centered and the scaled posterior distribution converges weakly to the conditional distribution of a supine functional of a Gaussian process U. Here I just used f star 1 as an example. Remember f star, because f star 1 is iota is immersion posterior using the first image map, and U is a Gaussian process is in this form, and H1 and H2 are two independent centered Gaussian process, and there is also a drift term, and divided by like the volume of the half rectangle from the lower left corner to the upper right corner, U and V. Okay, so we just that this H1 and H2 are two independent central Gaussian process, and the covariance kernel is like the H1 for H1 or H2, the covariance kernel is just like the intersection of these two, the volume of the intersection of these two hyperrectangle. And the special case is d equal to 1. We know that d equal to 1, the block estimator and the block estimator and the least square estimator is just the same. And when d equal to 1, we can write h as the sum of Brownian motion on each side. And W, remember this result we will use later. W is a standard Brownian motion, and starting from 0.
And sorry to interrupt. We have 3 minutes.
And L star is a special index that we only consider alpha k here. Alpha k along E is a unit vector, and this supin functional appear in the weak limit equals to another supin functional, but we can factor in distribution. But we can factor out the nuisance the nuisance parameters like g and all the derivatives of f0. When d equal to 1, the supin functional is equals to the slope of 0 of the greatest common exponent of w1 plus w2 plus t to the power alpha 1 plus 1. This is a traditional result from univariate asymptotic regression, and we can recover this result. And the limit coverage by studying the quantile of the posterior distribution, and given if we consider one-sided credible interval given a level of given a nominal level of gamma, this coverage is can be written as the second line here, and we use this relation. We can after subject f0 at x0 and rescaled because with only zero here is on the right side of the inequality, there's only 0, so the nuisance parameter doesn't take effect, and J is this universal quantity, and we can use J because we have 3 immersion map. We have 3 coverage. Z1 and Z2 are usually not symmetric about 1 or 2, but these 3, if we take average, its distribution is symmetric, and we can use numerical method to simulate the distribution of the ZB, and the value of the quantile can be used as call it recalibration method to get a shorter credible interval, but with the correct asymptotic coverage. This is a case in d equal to 2. We can see from the picture that the distribution of ZB1 and ZB2 are not apparently not symmetric, and ZB3 is symmetric. And similarly, we can use we give the value of the distribution. Some conclusion is here. Okay, the limiting coverage is slightly higher than the nominal credibility. This is not not very easy to obtain in parametric Bayesian literature, because we have Cox phenomenon that which states the coverage can be arbitrarily close to 0 in some random in some model. And also we need some fine quantile table of say B to apply the recalibration procedure to obtain a more or shorter credible interval. And immersion map, immersion posterior or projection posterior can also be used in other multivariate shape constraint problem. I think it is especially in multivariate case that the Euro shape constraint is not that strong enough to ensure a reasonable estimator. Yeah. So that's all for today.
Thank you, Kang, for this important work. Maybe we'll ask one question. Is there any question from the students?
Can I ask maybe a very naive question? So yeah, so here you have this constraint, and you use this. You call it projection or immersion prior. I don't know too much about the stuff. So okay, anyway, so I think there's recently I saw something like called post-processing posterior inference. How is this? How similar or different are these frameworks?
Sorry,
post-processing posterior inference. It's like you have some sort of constraints or some sort of property you want to have, like what you did here. You use unconstrained prior, and then you did this projection or something. Is this similar to the post-processing posterior inference?
Yeah, I don't know the name of, but the idea is here. Yeah, we use a unconstrained prior, and also often it's conjugate, so we can cast the unconstrained posterior easily, and then we project posterior to the desired parameter set.
Yeah,
that's the idea. Yeah.
Maybe it's just name the difference. Maybe it's the same framework. Okay.
Okay, I think it's the time to stop here. Thank our two speakers. Very interesting works. Thank you.
All right.